Okay, in this video, this is just a follow-up to the length contraction one. I said to you I'm going to talk a little bit about light years and how we can use light years as a unit of measurement. Look, in between the last video and this one, I just checked these numbers here. Now that thing there comes to 0.0958, and if you multiply it by 1900, it comes to about 180. But actually, the distance I told you about earlier, the height of Mount Washington, was 1910. So this comes to about 183. So I wasn't too far out, but it's contracted. Now, I'll just get rid of some of this. We don't need this now. And talk about light years. Now, we use the symbol Ly. Now, it's not a SI unit, unlike seconds and meters and things like that. This will be 10.1b. So I'll just get the numbering right, and I think this is about 276 or something like that. Okay, students often say to me, is this length contraction real or is it just imaginary? Now, I'll say it's real. Let me just show you a couple of things. Say you were measuring a meter ruler. Now, a meter ruler, of course, would be a meter. Now, let's imagine this is my meter ruler, stretched out to a whole meter, okay? And if it was moving at high speed past you, you would measure a contracted length because of this length contraction. Now, if you're travelling on the ruler itself, if you're going along with the ruler, so the ruler was in your frame of reference and you were at rest to it, you'd be measuring L0. So the ruler, a 1 meter ruler, would be L0 equals 1 meter. But if it goes past you and you try and measure it, you'd find it's contracted. So look here, I've got it down. It might be contracted to at speed. Now remember, it has to be relativistic speed. Now when we say relativistic speed in there, it's not really defined anywhere, but if you look at the effect of changing the speeds on L and L0, you'll find if you travel along at normal speeds, car speeds, plane speeds, rocket speeds, this would be still 1.00. It wouldn't change. You'd have to go a long way out of decimal places before you noticed a change. Once you get up to about 0.1 c, you'll start to see this change. Now you could confirm that for yourself, and I've done that in the textbook. I've shown you how as the velocity increases, this ratio changes and it becomes noticeable around about 0.c. c. So I've said in the book that relativistic speeds are when v is greater than, say, 0.1 c, and that's something pretty safe you can use. In an external exam, they wouldn't confuse you with that. They'd either tell you the speed and say it's relativistic, or it'd be obviously not relativistic. It'd be talking about a train or something like that. Okay, but you can use that as a rule of thumb. So at speed, it might be 0.60 meters. Now that's really contracted. So not only would it appear contracted, and students say, does it just appear to be contracted or is it really contracted? It is really contracted, because after all, you're measuring it, and what other basis have you got for determining whether it's contracted or not other than measuring it? Now, it's only contracted in the direction of motion. So this thing here, it was a meter ruler, but as it goes past you, it contracts in that direction. But what you'll notice, it hasn't contracted in the up and down direction, because that height, if you're looking at a pen, as that travelled at high speed past you, it would contract in that dimension. That's the direction it's travelling, but it wouldn't contract in that dimension or in terms of its width. So this piece of tape gets shorter in that horizontal direction because it's travelling that way, but it doesn't get shorter the other way. Look, you could probably show that with a ball. If this was going at high speed past you, Well, at rest it looks like that, perfectly round, but at high speed it'd squash up like that. Now its height would remain the same, and its width or depth would remain the same, but it'd squash up. Now I say to students, if I was running past you at high speed, I would contract in that direction, but my height wouldn't change at all. So I'd look skinnier, but the same height and the same width. And I've used a photo in the book, just one we mocked up somewhere in here, just to show a student running and then looking contracted, and you'll notice the height remains the same. Okay, so that's the main point for that. Now, when we talk about light years, look, I'll just talk about how you make use of these light years. Now, when Einstein first talked about this and developed his formulas, I mean, we wouldn't have had the sort of space travel and subatomic particle theory that we have now, but he would have done these calculations based on what he knew, and he used the idea of trains and things like that. Einstein, most of his work on the special relativity was done from about 1900 to 1905. He published the paper on special relativity in 1905. I was talking to a girl in my class a couple of years ago, and I said to her, he died when I was in year 1 at school. And she couldn't believe it. She said, I thought Einstein was around about 300 years ago. And she said it just seemed so weird that he was alive up until the middle of last century. She just pictured him as being ancient, as in like Newton's times. But he wasn't. He was around till the mid-1900s. He died in America about 1955. Now, the idea of light years, look, let's say we had this idea of going from Earth to Rigel, and it is 800 light years distant from one to the other. That's the distance, and we said that's L0. Okay. Now, if you travelled at half the speed, the question is, how long would it take? Now, if you did no other calculations, I just want to show you how to use this. If you travelled at half the speed, it would take you twice as long, because if you're going at the speed of light, it takes 800 years. If you're going at half the speed of light, it takes 1600 years. Now, the question is, if you're going at 0.5 c, you know the formulas are V is S on T, so T equals S on V. Now, if S is in light years and V is in meters per second, as in units of C, as in if it's in units of C, you've got things that don't seem to match up. Let's have a look. Say, for instance, you've got, this is 800 light years and the velocity is, let's say, 0.5 c. Now that comes to 1600 years. Now the question is, how can you cancel down light years and c? Now, you know, with this what we call dimensional analysis, you can cancel out the units, and they should come down to the units in the answer. Okay, but it would appear light years and c. Now, I used to say to my students, look, a simple way of doing this, it's not really legitimate, but a simple way is to just say a light year is just cy, and then the c's would cancel out and you'd be left with the unit of y. Now that's not really legitimate. Let me just show you how it should appear, but that's a quick way of doing it. This is that's light years, and this is this is c. Now c is just light travels at 1 light year per year. That's the definition of a light year. 1c is 1 light year per year. Okay, so that's all c stands for, light years per year. So in other words, light will travel in 1 year, it'll travel a distance of 1 light year. Now you can see these two things cancel out, and you're left with years to the minus 1, which you take to the top and it'd become years. So that's how you do that. So if you ever get a calculation where you're given light years, now I'm not so sure you will in the external exam, you'd have to, well, it's probably best to be prepared for it, because it's not such a hard idea. This light year, if you wanted to work it out, it's the distance travelled by light in a year, and when you think about it, it's a big number. I'll just do it once, just in case you're ever wondering how to convert it to meters, for instance. So it's basically the distance light travels in a year. So you know it travels at 3 by 10 to the 8 meters in 1 second. Well, all you have to do is multiply that by the number of seconds in a year. Well, there's 60 seconds in a minute, times 60 minutes in an hour, times 24 hours in a day, times 365 days in a year. If you multiply that all out, it comes to something like 10 to the 15. I did write it down, 9.5 by 10 to the 15 meters. Okay, I think you might, well, that's a the actual average number of days in a year. I think it's 0.24 or something like that, so you might have to do that. So that'd be converted to meters. Okay, I'm going to leave it at that. That's all we have to do for that. Thank you.